Well, I've been instructed not to roam because I'm supposed to operate the mouse here so that it's captured in the computer. I usually like to roam around, so. So I'll present to you today some information we have in a paper that's in press. It's a simple approach we've been using that's been quite effective, we believe, for being able to look at explanations of annual water level changes in the High Plains Aquifer. We also do modeling. For example, right now we're modeling one of the groundwater management district areas out in west central Kansas. Use mod flow and pest and various other equations that we put into the system to do the process-based type modeling. So we do it on both sides, both the simple approaches and then the much more complex approaches. But I'll give you this approach that we've developed here that seems to work very well and can explain 70 to 80% of the variation in the annual water levels in the High Plains Aquifer in Kansas. So, High Plains Aquifer in parts of 8 states. And Nebraska actually is the bathtub. It has the largest amount. I see that the following presentation will be on the geology and hydrology, so I assume we'll be hearing more on that. So Kansas has a significant portion of this, but not nearly as much water as Nebraska. I'll be talking mainly about the western portion of the aquifer, because that's the area where the water level declines are great. In other words, the approach is really not sustainable in terms of the water resource. It's more managed mining. Whereas, because precipitation increases across Kansas from west to east, these areas down here where there are 2 groundwater management districts, south central Kansas, are more manageable in terms of sustainability. The western part maybe not, but the eastern parts, yes. So they have a hope of actually sustaining water levels there. And we still have streams flowing in that particular area, but the streams have pretty well ceased to flow out here because we have captured the stream flow supplied by the groundwater discharge. Kansas measures over 1,400 wells annually in the winter, in January, when they're not pumping much, although sometimes we even find them pumping if they're trying to put some water into the soil. But those extend across the western part of the High Plains Aquifer and the south central part, mainly irrigation wells, but some other monitoring wells also. So we can use those to look at the annual change in water levels from one winter to the next. And in our particular program, we do go out and we have a select number of these. We check, measured twice. We have some idea of the statistical reproducibility of these, the quality of the data. So you'll see the aquifer decline here as you watched when we started the water level program, the Kansas Geological Survey and the Division of Water Resources together. The U.S. Geological Survey had been doing it before. So you see that developed. You can see the area of the greatest declines down here in southwest Kansas, and we have some of these declines that are certainly even over 100 feet, even up to 150 feet in some places. And then other areas of the aquifer where the declines aren't so great, but the saturated thicknesses also may not be as great. So another way of looking then at the the change from pre-development time, before irrigation really got started, and the present time, using an average of 3 years, is to look at the percent change in saturated thickness, and that's what's shown here. And you'll see we have some of these areas here that are dark, where over 60% of the saturated thickness is now gone. So they've mined over 60% of the aquifer in those areas. And generally where the those are shown. The aquifer originally had a smaller saturated thickness. So this is the aquifer we're working right now, modeling with ModFlow, groundwater flow model. And we finished doing this one. This one was modeled earlier as a part of our Kansas, Nebraska, Colorado lawsuit on the Republican River. So, and there's been modeling down in these areas as well. But today, again, I will concentrate on these particular areas. So what we've been doing is looking at the correlation of climatic indices with water level changes and then water level changes with water use. And some of the climatic indices we've used have been the Standardized Precipitation Index and the Palmer Drought Severity Index. Now you can see the 1930s and 1950s were especially severe droughts. The Standardized Precipitation Index is a shorter term index. You can see the longer term response of the Palmer Drought Index. And you can see the recent drought that Kansas had has not nearly been as severe as those in the past. Kansas has 9 climatic divisions, and these correlate fairly nicely with our groundwater management districts. Division 1 with GMD4, Division 4 with GMD1, 7, GMD3, and then Division 8 with the combined GMD2 and GMD5. So I'll be concentrating on this. Well, I'll first talk about these western 3, and I'll concentrate on the one closest to Nebraska. So on the left, you have 3 graphs that show the water level change per year, 1996 up to 2013. We do have the most recent data, but we have to process that more before I would show it on this graph. And then we have the dashed line, which is the change in the Standardized Precipitation Index. And you can see that they go up and down in general together. Now, if you plot the data from each of these 3 graphs to produce these plots of water level change versus the Standardized Precipitation Index, you can see that you get a pretty good correlation. The R squared ranges from 0.72 to 0.78. So again, we can use the Standardized Precipitation Index in this case to explain between 70 and 80% of the variation in the annual water level changes. So that is quite valuable because then we can use those regressions to predict what the water level changes would be for a future drought. So for example, suppose we had a future drought equivalent to the 1950s. And we can go and look at each one of these GMD areas, use the regression line, use the Standardized Precipitation Index for that 1950s drought period, and then predict what the water level decline would be, and then sum that. So you can see we get anywhere from maybe 6.5 feet to 16.5 feet of decline during a repeat of that particular drought period. So that's a valuable application. And another implication of this is, well, let's suppose we look at the 0 Standardized Precipitation Index value, because the negative values are when it's dry, and the positive values when it's wet. So if we have the 0 value, that's more the normal condition, more the average condition. So in that particular case, then we can go up on the graph, see what the point is on the regression curve, and then see what the water level decline would be. So we can see what the average water level decline would be for a normal climatic condition. And so you can see it ranges anywhere from about a decline of 0.6 feet or 0.57 feet here up to almost 2 feet, depending on the groundwater management district. Now again, I will, as I mentioned before, I'll concentrate on groundwater management district number 4, then the one closest to Nebraska. Now Kansas has had reporting of water use data for many years, and then since 19 1990, they've had a quality control procedure for checking that reported water use. So that's a little better. They see some spurious results. They go check with the farmer on that to make sure that we get the correct value. So that's a very valuable data set. So if we use that data set and then use our water level data, the data that we've been collecting with the Division of Water Resources since 1996, then we can we can plot that annual water level change versus the water use. But I'll just again show you and remind you, this is the same graph you saw as part of that one before, water level change versus the standardized precipitation index. And remember that we have very good correlation there, indicating that we have that climatic index being a good indicator of the driver of the water level change, which is the water use. And so then we actually then look at some of these points. You can see the drought period of 2002 to 2012 and a wet period of 2009. You can also point out 2006 and 2007. So in December, early January 2007, they had a lot of snow. It was difficult for people to get out and measure the well, especially when it was covered with a snowdrift. We're not going to be out there digging. So we had to go out, wait for the snow to melt some, and get out and actually make the measurement. Well, during that time, the water level had recovered a bit more. So that meant that when we looked at the 2006, 2007 measurement, 2007, 2008 values, then they were skewed one way for 1 year, one for the other. So if we remove those, we get a correlation that goes up to about 0.81, or we could do the average for those 2 years too. So we understand some of the variation in the data in these. But when we look at the water level change then with the annual water use, and I've shown this in millions acre feet, we also get a very good correlation. So R squared of 0.73. Being able to explain the annual water level change by 73% of that by the annual water use. So this becomes especially valuable because then we can look at what would be a sustainable water level. Well, that's a water level change of 0 in the system. And so if we look at that annual water level change of 0 and then come down here to the water use and then look at the average water use for that particular period, 1996 to 2013, then we can estimate the amount of pumping reduction that would be necessary to stabilize the water levels. However, when we look at what that means in terms of that district and the amount of water flowing to the water table to recharge that, in other words, to produce that sustainable water level, we find that it is greater than the estimated natural recharge. And so this has led us to investigate in more detail what's actually going on. And so we've discovered that it's very important to include irrigation return flow and enhanced precipitation recharge, which is when the soils are wet from irrigated areas, you get more recharge from rainfall, and then also drainage from the formerly saturated zone below which the water level has declined. There are low permeability units there. The water doesn't suddenly go zoom like it would in sand and gravel and coarse sand. In some of these fine-grained deposits, it takes a while. So we are now building into our process models, or mod flow models, this mechanism of delayed recharge and delayed drainage. So it has given us some insights on how to improve our models. Now, we have this local enhanced management area that just started up here in part of the Northwest Kansas District, Groundwater Management District, and the Kansas legislature passed a special law that allowed this type of system to be put in place. Now, our state Department of Agriculture Division of Water Resources can go in and put in special areas AGUCAs, they're called intensive groundwater use control areas. But in order to get the farmers really to do this more on their own, we had a law that was passed that allowed them to form their own unit, but then it has to be also sanctioned by the state. And if they vote within that particular area, a majority vote, then this becomes the law. Everybody has to follow this procedure, and they set up how much they want to reduce the pumping. And they set up one of average of 20% over 5 years. So that's the area here that is circled, where there's some groundwater, more groundwater pumping and greater water level declines in that particular area, called the Sheridan 6 area. So it started 2013. And the people in that groundwater management district saw our simple approach to doing things. And so now they have used that to see, well, how effective is that reduction in pumping in terms of fitting this water level decline and water use, the climatic indexes. And it's working quite well. For example, on the water level decline, water use correlation, we find that point fits very nicely. They've reduced their water use some, and indeed the water level change now fits that relationship. So we find now that the local groups are actually then using our simple approach. In other words, they don't have to suddenly try to come up with some fancy model to do this. They can get an idea of fairly large control on the variation in water levels just by looking at, say, the water use, and then also the predictive capability of the standardized precipitation index or some other climatic index. So that seems to be working quite nicely. So, major findings and conclusions here. You've seen some approaches here where we imply this the simple mechanism, a simple approach. This is in a paper in the Hydrologic Sciences Journal, and in press it's online. So we've seen that we can correlate the water level changes with climatic indices, and it works with other climatic indices too. This just seemed to work the best with this particular one. And the correlation also very good with water use data, or we do have good water use data. And some of the other groundwater management districts, we do have some problems in that some of the data has a lot more uncertainty in it. If they had changed, for example, from hour meters to flow meters, and we see some problems there. And then even in the kind of the climate of reporting, of how well people are reporting their data. We've seen that we could then look at the implications of the water level change and water use correlation and get an idea of what kind of cutback might be necessary. But in this particular case, we have to recognize that this is just going to be a temporary cutback, because as we begin to decrease the irrigation, then we'll have less irrigation return flow. And also, as we slow down the drop in the water level decline, then we will have less of this delayed drainage from the low permeability units. So we do have this slug of water that's coming through slowly that is giving this extra water above the natural recharge. And this provides then a bridge for individuals to be able to develop management schemes to try to reduce the amount of pumping. And this limited irrigation approach seems to be working quite well. Some of the economic studies have found that the farmers can adapt without too much loss economically with some limited irrigation. And I might just acknowledge that we have funding for this from our Kansas Water Office and the National Science Foundation, and a Ogallala Technical Support Program, also from the, in that case, from the Kansas, the state of Kansas water plan. And we do have a High Plains Atlas on our Kansas Geological Survey website. And if you want to look at the online paper, The easiest way is to go down here to this particular URL and then just search for my name. So that's the presentation to start the conference with today.